Okay, so we're going to skip 9.2 and we're going to go right to 9.3. Probability. You guys have done probability before. Probably need a little refresher on it. Some kind of keywords in here. Sample space seems to show up a lot. Sample space is essentially the possible outcomes of what your event is. Okay, and then we're going to be able to calculate probabilities and conditional probabilities, and you can kind of see all that, and we're going to do that. So first things first, find the probability of each of the following events. Okay, well, tossing a head on one toss of a fair coin. Well, it's heads or tails, so there's only two outcomes, tails and heads. So that's two outcomes. Now, one of those outcomes is heads, so the probability is 1/2. B, tossing two heads in a row on two tosses of a fair coin. Well, what are the outcomes? Well, I could get both tails. I could get tails then heads. I could get heads then tails. Or I could get the two heads in a row. Those are the only four things that can happen. So there are four possible outcomes. Well, how many of those outcomes give you two heads in a row? One. So that's the probability. Drawing a queen from a standard deck of 52 cards. Well, there's 52 outcomes. Now think about a deck of cards. A deck of cards has four suits: clubs, diamonds, spades, hearts. Okay? There is a queen in each one of those suits. So there are four queens in the deck. Okay? So that reduces to 1/13. D, rolling a sum of 4 on a single roll of 2 fair dice. Now, how many possible outcomes are there? Well, on the first die, there are 6 chances. Okay, 1, 2, 3, 4, 5, 6. On the second die, there are 6 numbers you could get. So there are 36 possible outcomes. Okay, now let's think about pairs of numbers that would get us a sum of 4. Well, 2, 2 is 1. You could get 1, 3. You could get 3, 1. Those are the only 3 combinations of dice that are going to get you 4. So there's 3 outcomes in our favor. So that reduces to 1/12. Okay. Now remember our lottery problem from 9.1. Guessing all 6 numbers in a state lottery that requires you to pick 6 numbers between 1 and 46, inclusive. Okay? Here's the thing. So we're going to fit E right down here. Now, we figured out 46C6, okay, in the last section. There were 9,366,819 combinations. Now, out of all those combinations, how many do you think win? Well, only one. Okay? So, I'm going to bring this up here. That means you got a 1 in 9,366,819 chance to win the lottery. So, in other words, don't buy lottery tickets. Okay? You don't got a chance. Okay? Save your money, especially young kids going to college. Save your money. Okay, this just defines what we just did, how to find the probability. Now I want you to notice here, the set of all possible outcomes of an experiment is the sample space. Okay, an event is a subset of that sample space. Okay, all right. Find the probability of rolling a sum divisible by 3 on a single roll of 2 fair dice. Now, when you roll 2 die, or 2 dice, you're going to get anywhere from 2 to 12, right? So, a sum divisible by 3, well, that narrows it down. 3, 6, 9, and 12 are your options. Okay? Now, what we can do is, now there are 4 numbers that we could get that are divisible by 3. So what I'm going to have is I'm going to have 4 probabilities. And I'm going to add them together. Now how many outcomes are there? Well, there's 36 possible outcomes. We talked about that in the first example. Okay. All right. So to roll a 3, how many pairs could I get to get 3? Well, there's only 2. Okay. 1 and 2 and a 2 and a 1. How many possible ways could you get 6? Well, there's 5. Okay, and you can write these out if you want to. Okay. How many options or how many possibilities are there to get a 9? Well, there's 4. 6, 3, 3, 6, 5, 4, 4, 5. And then there's only one chance to get a 12. Okay, sixes, pair of sixes. So if I add those all together, I get a 12 out of 36 chance, which is 1/3. Okay. The reason we add them is because any one of those 4 numbers is good for us. Okay. So we want to find each individual probability and add them together. Okay. So that's what I do for that one. Now, what this next slide talks about, essentially, okay, all the probabilities. So if you have, like for a die, okay, actually, no, let's do the coin. The coin's an easier one. Okay, there's a 1 in 2 chance you get heads. There's a 1 in 2 chance you get tails. If you add those together, you get 1. Think about it. 100% chance means definitely going to happen. Okay, so if I flip a coin, all right, I'm either going to get heads or tails. So something's going to happen. So I take each individual probability and add it up, and it should equal 1. Okay? If the probabilities don't add up to 1, you don't have a probability function. Okay? That's what this says. Okay? So your probability cannot be more than 1. And it can't be less than 0. So it has to be between 0 and 1. Okay? So it says, is it possible to weight a standard 6-sided die in such a way that the probability of rolling each number, n, is exactly 1 over n squared plus 1. So essentially this is what's going to happen. So you have your outcome, and then you have your probability. Hopefully I spelled that right. Now, if you're rolling one die, you're going to get 6 possible outcomes. You're going to roll a 1, you're going to roll a 2, you're going to roll a 3, you're going to roll a 4, 5, 6. Okay? Now, that's what n equals. That's what it says right there. So what you want to do is you want to plug each of those numbers into this. So if I plug 1 in here, let me show you how to do the first one, and then the others will just kind of naturally follow. So I have 1 over 1 squared plus 1. That's 1/2. If I plug in for 2, I get 1/5. If I plug in for 3, I get 1/10. If I plug 4 in, I get 1/17. If I plug 5 in, I get 1 over 26. And if I plug 6 in, I get 1 over 37. Now, all these added together, you add them. Okay? It doesn't equal 1. So it's not possible to do it. If it was possible to weight that die in that way, then all those probabilities would have added up to 1. They don't. So it's not possible. Okay. This example is going to make me hungry. Sal opens a box of a dozen chocolate creams and generously offers 2 of them to Val. Val likes vanilla creams the best, but all the chocolates look alike on the outside. If 4 of the 12 creams are vanilla, what is the probability that both of Val's picks turn out to be vanilla? Well, there's 2 things we need to do. Okay, we need to figure out the total number of outcomes. Okay, so my total number of outcomes, essentially, okay, if you want to think about it this way, is 12C2. There are 12 donuts, and I'm picking 2. Well, actually, I'm not picking them. Val's picking them. Okay? So, that's 66. So there are 66 different pairs that Val could pick out of that box. Now, on top are the number of outcomes that are good for Val. Okay? It says, what's the probability of that both of Val's picks turn out to be vanilla? Well, how many vanillas are there? Well, there's only 4. And out of those 4, she's got to get 2. Okay? So 4C2 is 6. So out of those 66 outcomes, 6 of them get her 2 vanillas. Well, 6 over 66 is 1 over 11. Okay? So again, on the bottom is the total number of outcomes. On the top are the number of outcomes that are favorable to us, or in this case, Val. Now, multiplication principle of probability. Okay? So it says, suppose an event A has probability P1 and an event B has probability P2 under the assumption that A occurs. Then the probability that both A and B occur, you just multiply the 2 probabilities together. Okay? If the events A and B are independent, we can omit the phrase under the assumption that A occurs, since that assumption wouldn't matter. They're independent events. A happens, B happens, neither one has anything to do with each other, and we move from there. Same problem. Same exact problem. Now, using the multiplication principle, here's what we have. Okay? What is the probability that, okay, again, we have Val's 2 vanillas. Well, let's look at it this way. Well, there's 12 donuts in the box, or creams. How many are vanilla? 4. So her first choice, she has a 4 out of 12 chance of picking a vanilla. Times, well, now once she picks the first vanilla, there's only 11 donuts left. Well, how many vanillas are left? 3. So I'm multiplying the probability that each pick will be vanilla. So if I multiply those, I get 12 over 132. Now watch what happens. That reduces to 1 over 11. So you get the same thing. So there's 2 ways to find it. You could pick the one that you think is easiest for you. This one's probably the easiest way, I think. All right, conditional probability. Now there's some work we got to do with this. Okay, it says if the event B depends on the event A. So now we're not talking about independent events now. We're talking, okay, event A has to happen, or event B has to happen, excuse me. Okay. 2 identical cookie jars are on a counter. Jar A contains 2 chocolate chip and 2 peanut butter cookies. Jar B only has 1 chocolate chip cookie. That's it. We select a cookie at random. What is the probability that that is a chocolate chip cookie? So what we're going to have to do is we're going to have to make what we call a tree. Okay? Not with leaves or anything, but okay. So here's my cookie. Now there are 2 choices here. Okay? I can either pick from jar A or I can pick from jar B. Okay? Now, what are the chances of me choosing jar A? Well, 50%, so 0.5. Just like there's a 50% chance that I could choose jar B. Now, in jar B, let's do the easy one first. In jar B, there's only 1 cookie, chocolate chip cookie. All right? So there is a 100% chance that if I choose I keep saying char. There's a 100% chance that if I choose jar B, I'm going to get chocolate chip cookies. Okay? Now, the probability of me choosing jar B and getting a chocolate chip cookie is 0.5 times 1. You take these 2 probabilities and you multiply them together. So the probability of me choosing jar B and a chocolate chip cookie is 0.5. Now, jar A has 4 cookies in it. 2 of them are chocolate chip. 2 of them are peanut butter. Okay? Now, if we choose jar A, well, there's 4 cookies. So the probability of picking any one of these cookies is 0.25, right? 1/4. Okay? So what we have to do now is, what is the probability of choosing jar A and a chocolate chip cookie? Well, what do? I take the probability of choosing jar A and I multiply it by the probability of once I'm in jar A, there's a 25% chance. So that's 0.125. Well, that's the same thing here. Okay, actually all of these are 0.125. Okay. So, the question was, what is the probability that it is a chocolate chip cookie? Well, there are 3 scenarios where I get a chocolate chip cookie, and here they are, and here are their probabilities. So I'm going to take 0.125, I'm going to add 0.125, and I'm going to add 0.5. Okay? So I'm going to get 0.75. Now what does that mean? Okay, that's 3/4. So I got a 3 out of 4 chance that I'm going to get a chocolate chip cookie out of one of those jars. Okay, now that's important to note because it says in example 8. Now that was this problem. We just did that problem. Now we look at 8. It says, suppose we've drawn a cookie at random from one of the jars described in example 7. Given that it's going to be a chocolate chip cookie, what is the probability that it came from jar A? Now, this is where we want to use this formula. So the probability of a chocolate chip cookie given jar A. So given jar A, it's chocolate chip. Notice the order. So this is the probability of jar A and chocolate chip. I'm using CC, I'm out of room, over the probability of getting a chocolate chip. Okay. Now, we go back to our tree. What was the probability of picking jar A? 0.5, right here. So that's 1/2. We'll just call it 1/2. Times, what was the probability that once I was in jar A, there's 4 cookies. 2 of them are chocolate chip. So, 2 out of 4. Over the probability that I got a chocolate chip cookie, period, no matter what jar. Well, that's what we found. We found that. So that's 3/4. Okay, I'm out of room. So I multiply on top, I get 2/8. Now I'm dividing by 3/4, so that's the same as multiplying by 4/3. So that's 8/24, which reduces to 1/3. Okay? So that's how you figure out conditional probability. Again, another long video, but again, if we get the basics down, we should be okay. All right? So that is 9.3, probability.